So in today's lecture we are going to discuss the lattice vibration of one-dimensional diatomic lattice. So in the previous lecture we have considered one-dimensional monatomic lattice. So in this lecture we will discuss one-dimensional diatomic lattice. For example, you take an NaCl. So now let the mass of the two atoms will be small m and capital M, and this small m is less than capital M, and the distance between the nearest neighbor B will be A, and let these atoms be placed along your x-axis, and they are placed at the sides 2n minus 1, 2n minus 2, 2n minus 3, and 2n plus 1, 2n plus 2, 2n plus 3. So now there is one important thing, that this smaller mass is placed at even number site, that is 2n, 2n minus 2, 2n plus 2, and the odd number is placed at the bigger one is placed at the odd side numbers. So now let x2n represents the displacement of this 2nth site, and the other assumption being made as that for monatomic lattice. Now we proceed as the same as the monatomic lattice. जैसे हमने monatomic lattice के लिए प्रोसीजर किया था, वैसे इसी diatomic lattice के लिए करेंगे. Now this is along x-axis. This is your equilibrium state. And this will be your strained state. जब लिक्विड स्टेट में क्या कोई फोर्स लगाएंगे एक्स डायरेक्शन में तो क्या होगा, देयर विल बी lattice vibration and there will be displacement of the atoms about their mean positions. So now we will find out the equation of motion for each type of atom, that is small m and capital M. So now as the same procedure जैसे हमने पिछले टॉपिक में किया था, हम क्या करेंगे, यहाँ से क्या करेंगे, फोर्स कैलकुलेट करेंगे. Now as the same procedure we have calculated the force. Force is according to Newton law. This is mass into this your xn, and this is beta is spring constant. This is we have calculated in the same procedure yesterday, and this is if you calculate this, then you can put n plus 1. There will be 2n plus 1, there will be 2n plus 1, and 1 will be added there, 1 will be added there, this will be less, and this will be 2n plus 1. So here is 2, and because we are dealing with diatomic molecule. So now we will assume a equation for this. So now equation will be the solution of these equations are assumed to be, that is x2n. This will be of exponential form. Sorry, this is your double derivative of this. Double derivative here, double derivative this. Dot means, for this double dot means d square x upon dt square. Double dot means double differentiation with time. So this will be minus 2 k n a, where omega is the angular frequency of this simple harmonic motion of due to the displacement of this x2n, and k is your Babe number, your propagation constant, and is your numbered side. 2n plus 1 will be simply here, this will be n plus 1 minus 2n plus 1 ka, and a is here is your spacing between your nearest neighbor atoms, that is this a. So now here we will assume that the both the particles participating in single wave motion and frequency for both type is taken as same. Frequency for these both atoms will be same, but their amplitude may be different because of the difference in their masses. जब मास क्या होगा m डिफरेंट होगा दोनों पार्टिकल के लिए, तो क्या होगा, their amplitude will also be different but the frequency might remain same. So now here this will be beta because their amplitude will remain different. A and B will be different due to different mass, that is m less than capital M. So now by using these equation 1, 2, 3 and 4 we will calculate this. So now I have put these values of xn2 x2n plus 1 and x2n plus 2 into this equation, and this means double derivative with respect to time. So by putting this I have calculated this in terms of exponential. Here this is there is one mistake, there is a capital M, and so by calculating this I have get this. Now by simplifying this, because here this is m d and double derivative of x2n with respect to time, this will be differentiating. There is iota square and omega square. There will be iota square will be -1, omega square and exponential this, and beta putting the value of x 2n plus 1, 2x minus 1 and 2xn 2, putting this into this equation, and similarly differentiating with respect to time, double time, this will be minus omega square into b capital M, and putting the values of these values in terms of their exponentials. So now I will simplify this. So now I have simplified this equation into these simple equations. So now to solve this, because this is in terms of exponential, so now we can multiply and divide this term by 2, multiplied and divided by this term by 2, and divided by 2 for this whole term. This, so this becomes, as we know, this becomes cos iota ka in terms of your exponential function. So this will reduce as beta b cos ka minus 2 beta a, and this will be omega square m b, this is b not beta, this will be 2 beta a into cos ka minus 2 beta b. So now this term, this coefficient, this is the coefficient of b, this is the coefficient of b, take this side. So now this equation, these equation will reduces to 2 beta omega square m common a, and take the to this side, this will be minus 2 beta cos ka. These are the coefficient of v. This equation will rearrange like this. This equation will also be rearranged like this, 2 minus a वाला टर्म इस साइड आ जाएगी, तो हो जाएगा माइनस 2 बीटा cos ka this will be plus 2 beta minus omega square m to b is equal to 0. Sorry, here is a coefficient is here. This equation will becomes 7, this is 8. So now these equation 7 and 8 have non-trivial solution if their determinant the determinant of coefficient a and b will be 0. So now you can write this in terms of determinant omega square minus 2 cos ka. This is for coefficient A, this is for coefficient B. So if their determinant is equal to 0, so they have fruitful solutions, non-trivial solution, useful solutions. This is equation number 9. So now by using determinant, this we have calculated. So now multiply this by this, we have by solving this product we will have this type of equation. So the highest coefficient, power coefficient is this small m, so take this as forward. This will have omega 4 and this is same, so this will be added. So this we have calculated. So now this is the highest power, so this and this will be clubbed, this will be 4 beta square will be common, and this will be 1 minus cos square k. This is sin square k, this factor is there. So here 2 beta omega square will be common and small m and m will be added by taking minus sign common. So this will be the resulting equation. So this is your equation in quadratic in the omega square. So this is equation number 1. So this equation is quadratic in omega square. You can write this omega square ka square. This will be quadratic with omega square. This is quadratic in omega square. So this equation is quadratic in omega square. So thus omega square will be, we will find out the root, and the formula is minus b plus minus under root square coefficient of this b square minus 4ac divided by 2a. That is the formula for this. So by putting this formula I will solve this. So now I have put the formula. This is minus of 2b, this minus plus this formula, plus minus b square whole square of b minus 4 into a is 1, 4 into this c, a is 1, this c value c, 4 into 4 16, and this value c into 2a. A coefficient of a, this is 1, this is 2, and I will take common 2 common, and there will be beta 1, this factor, and this whole factor will come down, beta will be common, this will be whole square of this, and minus this 4 sin square k divided by 2. So now by solving this root for this omega square, we have plus minus here, so therefore we have two values for this omega square, that is omega square plus, this omega square minus. This is given by question number 12 and question number 13. So now we will find that if this ka is very less than 1, so then this sign ka can be neglected, because suppose this is approaches to 0 and this is very small, so this also will be 0, means this is very small, and since sin k is small, then its square will be much smaller, so therefore this can be neglected in this expression. So therefore omega plus will be, this will be neglected, then the square of the under root, then this will be under root, sorry, but first of all square, this will be beta m plus capital M, square will be neglected by this under root beta plus 1 by m, so this will be 2 beta by m plus 1 by capital M. So omega plus will be under root of 2 beta by m plus 1 by capital M. This is small m, this is capital M. Question number 14. So now for another condition, for k greater than pi by 2a, these two conditions we have found for a large frequency or for small frequencies. The sign k will approaches to, suppose this is pi by 2, sin pi by 2, what is sin pi by 2 is equal to 1, so this will approaches to 1, so thus we have omega plus square will be, this will be 1, so we will have beta 1 by m plus 1 by beta under root 1 upon m, 1 upon capital M whole square plus 4, this will be 1 m into capital M. So now if we solve this, this will be beta by m plus 1 by capital M plus beta, this will be whole square, so कर लेते हैं इसको 1 by small m square plus 1 by capital M का square plus 1 by 2 ab, this will be 2 m 4 m. So if this is less, this will be minus 2 upon mm, so this will become a minus b का whole square. So this will become 1 upon 1 minus plus beta, this under root cancel by square, so what this will come, so this is plus, so what this will be cancelled, so you will remaining term will be 2 beta upon m, and if you put the under root from here, this will be 2 beta upon m. This will be question number 15. By similar procedure I have calculated for the expression for omega minus. So now from the question number 13 we have the value of omega minus, that is, this is the value of omega minus. So now in this case I will take that is k approaches to 0, that is ka is very less than 1. So for ka very less than 1, your sin ka is equal to ka, because sin 0 is equal to 0, so therefore k is small, this will be equal to ka. So now I will take, for example, this common from this bracket, there will be it common होगा तो क्या हो जाएगा, स्क्वायर क्या हो जाएगा, सिंपल बाहर आ जाएगा, ऐसे बाहर आ गया, and there will be 1, and if I solve this, this will be this, and because sin Ka is equal to Ka square, sin Ka square will be Ka square, this will be cancelled. And also from here, when you rearrange it, also take this common into this whole equation. This will be 1, this will be minus 1, and this term, and this will be whole term, this is under root. So now I will take I will expand this binomially because here K is very small. Binomially expand करूँगा तो क्या हो जाएगा, this will be 1/2 into this term, the 2 will be cancelled, this will be 2, and plus this will be whole square, this will be 16, and K4 A4, that term will be here, and because K is small, there K raised to power 4 will also be small, therefore higher term will be cancelled. Therefore resulting equation is this. So now I will take a pi by 2 into a, that means Ka, when Ka approaches to 1, because sin Ka will be Ka, and Ka approaches to 1 in this case. So here I will take omega minus will be in terms of root 2 beta upon m. This further equation will be reduced to this. Here m is greater than m, so therefore this equation will be reduced into 2 beta upon m. As that w plus was reduced into like this, w plus was under root 2 beta upon small m, is small m की term में थी, w plus omega m plus and omega minus is in term of capital M, that is for heavier mass. So now by using these equations I will plot a graph between omega and k. So now by using that solution, that particular condition for your omega plus and omega minus, by equation 14, 15, 16 and 17, we obtained the particular band for your, that is as one-dimensional diatomic molecule, so lattice. So now this your so now here we observe that the allowed frequency of propagation are split into two branches. First is your lower is acoustical branch and upper branch is optical branch. So now this acoustical branch is same as in monatomic lattice, but this optical branch represents the different type of wave motion. So now here we notice that between these two branches there exists a band of frequencies for which the waves like solution, these are wave like solutions, are not allowed and they are not possible. This means it is not possible to excite the lattice vibration with frequency lies in this region. Hence this band is named as your forbidden frequency band. The width of this band depends upon the mass ratio, that is small m divided by capital M. If the ratio is large, then this band is more wider, and if mass ratio is unity, then these two branches will meet each other. This will meet each other when this mass ratio is unity. Then they will join at your plus minus pi by 2a. That means they will join, then there will be degeneracy condition. That means this band, this forbidden frequency band will disappears. And also we know that there is a first Brillouin zone which lies in the condition minus pi by 2a k into pi 2a. The first Brillouin zone lies between these conditions.